This is a tutorial on how to design your very own CPU. Requirements: no binary, logic gates, and want to build a CPU. If you have these three, get a pencil and some paper because today you're going to design a CPU. First, create the ALU. The ALU, or Arithmetic Logic Unit, is the math part of the CPU. It does stuff to numbers based on the instruction it is given, like add or subtract. Create an arrow-like shape and put on it a label of ALU. Second, create the bus. The bus is a shared data line that allows components to communicate with the ALU. Put a strike through the bus line and label it with a number to specify how many wires are in that line. You may also notice that it is not very curvy, as it is easier to model with sharp corners than floppy wires. Third, registers. The ALU has a problem. If the bus has a number on it, both A and B will both be set, then added, then output back into the bus. The output will be added again, and it's just an infinite loop. Registers can either have a set signal, a read signal, or both. The set signal sets or saves the contents of the register to whatever was going into the register. If the set signal is off, it cannot be changed by a change to the input. The read signal only outputs the value being inputted if the signal to the read is on. Fourth, add the control unit. The control unit is probably the most important part of the CPU, as it controls all the microcommands that execute in the CPU. For example, you'd like to load register A to a number. This takes two microcommands. First, output the number you'd like to save onto the bus. Second, set the register A to the bus. Side note, lines that cross aren't connected unless they use arrows. All of the commands on the CPU execute because of the control unit. Fifth, connect a ROM to the control unit. ROMs stand for read-only memory, or just memory that you can read from but cannot write to in code. The ROM holds all of the instructions for the control unit and sends out an instruction when given an address. Sixth, the PC register. PC stands for program counter, which keeps track of the current line of code being executed. In order to keep track of it, you need to make a read and write register that can be set when given a signal to set. You also need an add signal which will be tied to the clock, and the add signal just adds 1 to the instruction address. With this piece of technology, you can now jump to a line of code in your program by setting the address in your program counter. Seventh, the output line. The output signal will be used for peripherals that can be controlled by the CPU. As you can see here, the bus connects with the output register using this dot showing that they're connected. Add an input line to read anything the peripherals send. Eighth, create the clock. The clock is what the control unit, program counter, and ROM runs on. A clock signal works like this. First, add 1 to the program counter to get the next instruction. Second, execute the command currently in the control unit. In another tutorial where we add the RAM module, I'll show how the clock can have a couple other functions. Lastly, create the instructions and wire them. As I did earlier, you can just make a load B data command and create some of the other ones. Some instructions include add, subtract, load output A, load output B, and jump if 0. In order to wire them, you take the instruction needing to be executed from the control unit and wire it into any components that need to be turned on or given data. In this case of the add command, you have to save the ALU state, either its output or the current instructions of the ALU, like add or subtract. This is the end of the design tutorial, but later I will implement this architecture in Minecraft with working RAM and cache modules. With that said, the architecture of the CPU is not the only one that exists, but a very simple one that I have developed. Lastly, I made this video because I feel that there's a deficit in short, get-to-the-point tutorials. The ones I found while trying to make my own CPU were all like 3 hours long, and I decided to just make one off of a Google image rather than watching a YouTube video. Hopefully this video fills the gap for people like me who just wanted to know how to make a CPU. Thanks for watching, Happy Christmas, and Merry New Year.